Okay, so we were talking about applying the energy equation by using the Reynolds transport theorem on the specific energy E. Okay, and just here we talked about an error in sign. The error is not in this equation, it is in this equation, and I will explain why. So here you have Q dot minus W dot equals to the variation of energy with time over the control volume. Here we should have minus summation of E dot inlet and plus summation of E dot outlet. So whenever to always to know if your signs are right or not, go back to the physics and go back to your Reynolds transport theorem. If we go back to the Reynolds transport theorem, this term is due to the fluxes of energy crossing in and out our control surface. And we have seen that this term is calculated as follow. It comes from integral over the control surface, okay, of rho times the property. Here we are studying, which is E, which is the specific energy, times V dot N dA. Okay, and again, always remember V dot N is positive for outlets and is negative for inlets. This is why we should do minus summation of energy fluxes crossing the control surface inward and plus sum of energy fluxes going outward. And how we can physically interpret this? So I'll give you a small example. Let's say you have steady state application. If you have a steady state application, this term will cancel out, okay? So let's say you provide heat to your system. So physically, what will happen is that a flux coming in will gain this energy and will take it with it out. So the energy of the outlet flow will be larger than the energy of the inlet flow because it will absorb this heat. And it will absorb it because if it will not, we don't have a steady state application. So if you want, for steady state applications, when we provide heat, the energy of the outlet flow will be larger than the energy of the inlet flow. So then let's say Q dot, we don't have work, Q dot should be equal to energy out, flux of energy out minus flux of energy in. Now, in other terms, if also we have a general application, it's unsteady, how we can do the interpretation here? What we are giving to the energy given to the system, okay, which is Q dot minus W dot. And this energy can be given in form of heat or work rate. If we give an energy to the system, this energy can be divided into two parts. It can be accumulated by the control volume if we have transient application, and the remaining part will be carried out by the flows that are going out. So this is how we can make sure that physically we should have here a minus and here a plus, because energy provided to the system will be or accumulated by the control volume or will be carried by the flow. Okay, so I will fix this for you in the slide. So this is plus and this is minus. And now, if we apply it for steady flow with uniform single inlet and single outlet, what will happen? First, this term is transient term. Whenever I have a steady application, the transient term will cancel out. And I will then have plus summation of energy fluxes that are going out minus summation of energy fluxes that are coming in. Now let us do interpretation how these terms will be written when we have flow with uniform single inlet and single outlet. So I have one inlet, one outlet, and I want to find the expression of my E dot out and E dot in. So I go back again to my formula. So the energy dot is given by integral of rho times, as we have seen together before, that when we write the energy equation, okay, here we will have what? We'll have the term of enthalpy. Okay, so it's rho, because if you remember, if you go back here, we have seen together that when we do integral over the control surface, we'll have the enthalpy plus half V square plus GZ times rho times V dot NdA. Okay? If you are working in steady state applications where we have uniform conditions at inlet and outlet, when I say I have uniform conditions, so everything for one cross section, everything will remain the same over the control surface. This means that if I'm considering the outlet, at the outlet, I have certain properties, H out, V out, okay, plus GZ out, times rho V dot N at the outlet. So as we said, we have uniform properties. I will take them outside of the integral. So what do I obtain? I have rho times enthalpy plus half V square plus GZ, okay, and I have times for an outlet V dot N. So since we are considering cases where the velocity is perpendicular to the surface, when you do V dot N for an outlet, so this is N, this is V, they are same sense, okay, V dot N will give you just V, so times V times integral dA. Now, what is integral dA? Integral dA is the area of the cross-sectional we are considering, of the outlet. So now what do I obtain? I obtain a rho, so this is equal to rho times V times A, and this is what? This is m dot, okay? This is m dot at the outlet. Times what? Times this term, okay? If you take rho inside, okay? If you take rho inside, you will get the following. It's m dot times rho times h. Now we have seen together that what is h? H is U, so internal energy, plus P over rho. Okay, so plus rho V square over 2 plus rho GZ. Okay, so the whole term times m dot, as we have considered this here. So this will give me the energy flux that is going out. Okay, now as we talked about, when we consider small variation of temperature or constant temperature, if I'm dealing with a fluid, let's say water without phase change, okay, which is in general in majority of application I have this, then I can neglect the variation of internal energy. This is why I can neglect this term. Okay, so then what do I obtain? Now if I do here rho times P over rho will simplify, but I will get the following. I will get m dot times P plus rho V square over 2 plus rho GZ. And now this is, if you go back to the expression, this is what I obtained here. So the flux, the energy flux that is getting outward, okay, is given by the following. So it's m dot over rho times P plus rho V square over 2 plus rho GZ. Okay. So now, y over rho, because as I told you, we got one rho inside of the bracket. So when you got one rho inside of the bracket, you should do m dot over rho, since m dot is rho times V times A. Okay. So if you replace rho VA by m dot, and you want to take one rho inside, you should multiply by rho and divide by rho. Okay, this is why it's m dot over rho times P plus rho V square over 2 plus rho GZ. Or if you want, you can remove, if you want to remove this rho here, you should take it inside. So you put P over rho plus V square over 2 plus GZ, which is the expression we got together. Okay, And then for the outlet, you will have similar term, but just you will have a minus because V dot N for the outlet is minus V, okay? Because we have already seen together that if we have an inlet, okay, if V is crossing perpendicular, the cross section in a perpendicular way, and this is N, V dot N will give us a negative result. This is in general the cases. In general problems, we have velocity profile perpendicular to the surface. If it's not, and in some cases, you might have let's say a velocity inlet that is inclined. So all you have to do then is to know what is the angle theta here, okay? And when you do then V dot N, you will do, and this is N. So it's like you are projecting V on N. You'll obtain minus V, but you should multiply by cosine theta. But in the majority of cases, theta is 0. This is why here we are developing for the case where V is perpendicular to the surface. So V dot N is minus V. And therefore, this is our energy flux. So this is our energy flux out. And this is our energy flux in. Okay. And now we want to apply this equation for a certain problem where we have a pump, a turbine, and we have friction forces. So what will happen? We should evaluate this term, W dot. Okay. So for W dot, as we said, a pump is putting work on the system. So if we use this formula, this equation considers that every work that we put on the system is accounted as a negative work. So I should replace W dot by minus W dot pump. And since the turbine is producing work, okay, then I should put plus W dot turbine. And since friction will cause a loss of energy, so I will have, or if you want, the work of friction will be delivered to the environment, so it's out of the system. So also I should do plus W dot friction. Okay. So now, don't forget that you have a minus outside. You have a minus outside here. Okay. So you should do, if you take the minus into consideration, you will obtain plus W pump minus W dot turbine minus W dot friction. So all of these are absolute values. W pump, W turbine, and W friction are in absolute value. And the sign will give you if we should subtract or add it. So since we have, as we said, the minus here, we'll take it inside. And then we'll have plus W dot pump minus W dot turbine minus W dot friction equal to the flux of energy out minus the flux of energy in. And we can make sure that this is very physical. How we can do it? A pump will deliver work to my system, so it will try to raise its energy, okay? Or, so this work delivered can be interpreted in two ways. Or it will accumulate energy in my system, but this is not the case here. Why? Because I'm dealing with a steady flow. So what will happen then? This pump work will be transported by my fluid. So it will be gained by the fluid that is crossing over. So this is why it will increase the energy of the outlet flux. The outlet flux will have an energy larger than the inner flux due to the work of pump delivered. On the other hand, okay, for the turbine and friction forces, they will do the opposite. They will try to reduce the outlet energy flux, okay, because they are lost. So W turbine. Okay, for a turbine, what will happen? The turbine, okay, it will lose energy. Whenever I have turbine, it will lose energy. The system, my system, okay, my will lose energy. This is why what will happen is that this will tend to decrease the energy of the outlet flux compared to the inlet flux. So always, if you want to be able to imagine the situation, you can just do the analysis. If I only have a turbine, what will happen? If I only have a turbine, okay, since my turbine will try to deliver work to the outside, okay, then if I have a transient application, sorry, if I have a steady application, this means that I don't have uh, accumulation or loss of energy from the system. Who will lose then? The flux that is coming out will lose energy relative to the flux that is coming in. So this is why in this case also this is physical. So it should be minus W dot turbine, because for the turbine will tend to take energy from my system. Therefore, energy out minus energy in balance will be negative. Okay, because imagine that this is your, let's say, your turbine. You have a flux that is coming in and another that will go out. Since your turbine will deliver work, so you have, your system is losing this energy, and it will take it from what? It will take it from the crossing flow, because we don't have any transient term here. You don't have any energy accumulation or loss in your control volume. So your only source in steady application, your only source of energy will be the flux that is crossing your control surface. So since I have a work that is delivered to the environment and I have a steady application, then this energy will come from the crossing flux that is coming in. So I will take a part of its energy. This is why for the flux that will be out, the energy of the flux out will be lower than the energy of the flux in if I just have a turbine. Now, if you have in a system combination of pump, turbine, and friction, then the pump will tend to increase the energy of the outlet flow, while the turbine and the friction forces will tend to reduce the energy of the outlet flow. So in total, I have plus W dot pump minus W dot turbine minus W dot friction equal to the energy rate at the outlet minus the energy rate at the inlet. Okay, now we can, so as you can see here, this is the system we were talking about. You have an inlet flux and you have an outlet flux. And between the inlet and the outlet, you have a pump, you have a turbine, you have a friction. So what will happen is that where at the pump level, work is delivered to the system. Okay, so it's entering the system. The pump will tend to increase the energy of my fluid, while the turbine will tend to decrease it because it will deliver work, a rate of work to the external environment, to our system. And plus, the friction will also lead to losses. So this is W dot friction. Okay, so now I can do interpretation of my formula. So since I'm considering now absolute values for W dot pump, W dot turbine, and W dot friction, at the end, what the pump will tend to increase. So it's plus W dot pump, it's minus W dot turbine, it's minus W dot friction equals to the energy rate at outlet minus energy rate at inlet. Okay. Now, sometimes we express our terms as head, pressure head. Okay, so what do we, as head, we have head of pressure, we had head of pump, we had head of friction, etc. What do we mean by this? It's very simple. We have written our energy equation in the following form. So for our previous example, the energy equation was in the following form: W dot pump minus W dot turbine minus W dot friction equals to m dot over rho times P plus rho V square over 2 plus rho GZ. Okay. Now, if you take this term into factor, okay, rho g, if you take it outside the brackets, what do you get? You will get m dot times rho g over rho. Rho will simplify, will cancel out. So you have m dot times g times what? So since we consider we will take into factor rho g, so we'll have p over rho g plus v square over 2g plus z. Okay? Now, all of these terms will have the same unit, because you know, whenever for an equation to be physical, when I add terms, they should have the same unit. You have that the unit of z is meter. Okay? So v square over 2g is also in meter, and p over rho g is in meter. So we call these terms head. So this is the pressure head. This is the kinetic head. Okay, and this is, if you want, this is due to, this is the height variation. This is hydrostatic head. Okay, so we can term, instead of if you want, talking with about pressure terms, we'll work about head. Okay, so in general, we can write the equation in the following form. And since we have done this for this side, we will do it also for the side, for the left hand side. So here, if we also take rho g into factor, okay, the m dot g is, okay, so here, if you want, as we did here, okay, we'll do the same procedure for the other term. So here, what you will get when you have considered rho g outside, we got m dot times g. Okay, so times a certain term. We'll do the same here for the left hand side. If we take m dot g into factor, we'll obtain the following. We'll obtain w dot pump over m dot g, w dot turbine over m dot g, and all of these terms also will have the unit of meter. Okay, so in this way we can express our balance as a balance of heads, and it will be represented in the following way. So we will name w dot friction over m dot g, will name it friction head. W dot pump over m dot g is the pump head. W dot turbine over m dot g is the turbine head. Now, since here P over rho g is related to pressure, we call it pressure head. V square over 2g is related to motion of the fluid, so we call it dynamic head. Okay, and then what will happen is that we can simplify m dot g from both sides. So here, since you have taken m dot g into factor in for all your terms, then you can simplify it. And what will be your equations then? It will be just an equation of heads. So head of the pump minus head of the turbine minus head of friction is equal to P over rho g plus V square over 2g plus z at the outlet minus P over rho g plus V square over 2g plus z over the end. Okay, so just this is a way to write the equation in terms of heads. Now look, what will happen if I don't have any device, any pump, any turbine, and if I don't have friction, I don't have losses? What will happen? I will obtain, this is the Bernoulli's equation. Okay, so you are familiar with Bernoulli's equation. So, and you know that the assumptions for Bernoulli's equation is that we don't have any external intervention, we don't have any equipment that is providing work or that is delivering work to the environment, and we don't have losses. So if these conditions are covered, then what will happen is that we will end up with conservation of energy, if you want, for our flow. So the energy of the inlet flow will be equal to the energy of the outlet flow, and we can write what the common Bernoulli's equation that we use a lot. Okay, so here, if you want, this is the most general equation, and in particular cases, so we started from Reynolds transport theorem. We started by the most general equation, and then we applied it first for a certain case where we have steady flow. Then we considered 1D inlet and outlet. Then we considered if we don't have any intervention of pump, turbine, or any losses, then we end up with Bernoulli's equation. So all of these are certain applications of the general energy equation. Now we will just do some problems to practice on the energy equation. So we have a pump that delivers water at a steady rate of 300 gal per minute. Now don't worry about units. Whenever you have units, you will try to convert them to the, so here you can work in English units, for example. Okay, and if you have, let's say your data is given in meters and it's given in as pressure, you have them in Pascal, then you can work in SI systems. So we have here that the pipe diameter is 3.5 inch and the pressure is 18 psi at section 1, while for the downstream pump we have a pipe diameter that is 1 inch and a pressure that is 60 psi. The change in water elevation across the pump is 0. The rise in internal energy of water is given to be equal to 93 feet times LB per LBM, and the pumping process is considered to be adiabatic. So look here, this is an example where we have a variation in internal energy. If we have a variation in internal energy, they should give it to us, or they should give us what is delta T, and we go to tables to find the corresponding change in internal energy. So as I told you, in general, for the majority of applications, this change is negligible. But if it's not, they will give us information about it. Or they will give it here as it is, or they can tell us what is delta T. So if we know T1, we know T2, the rise in temperature between 1 and 2, we can go to the tables of water. We can see at T1 what is the internal energy of the flow, and at T2 what is the internal energy, and then this will allow us to calculate the variation of internal energy. So since here the variation of internal energy is not negligible, we should go back to the basic equations, which will use the enthalpy. Okay, the enthalpy is U plus P over rho. We said that if the change in internal energy can be neglected, then we can just consider replace H by P over rho. If not, we should take the both terms. Okay, so here always start by the general equation. Put your general equation and they apply term by term to see if you know them or if they are unknown. So in your equation, you can allow for one unknown because it's one equation. So this, whenever you replace all your variables, you will end up with one unknown. In case you have more than one unknown, you should try to write another equation. And the other equation in general, you find it from what? Always remember, don't disconnect conservation laws. You should always combine them. So you will always need to apply continuity equation, because continuity equation can give you a relation between velocities. So if one of the velocities is unknown, if you know one, you can find the other. Let us see how. So I will start first by writing the general energy equation. So which is the following. I have m dot times, so here first it's a steady application, okay? Because whenever here they gave you a steady state, they told you that it is a steady rate. So since I have a steady state application, then the transient term will cancel out, okay? And I only have one inlet, one outlet. So I can just say now that the energy provided to my system, which is Q dot minus W dot, okay? And when I put minus here, what is the convention? Everything that I put on my system, okay, is a negative work. So here, if you want W dot will represent minus W dot of the shaft. And minus minus will give you plus. So if you want then, when you do minus minus W shaft, you will get plus W dot at the shaft. Okay, so Q dot plus W dot at the shaft is equal to M dot. So now, since we have steady flow, M dot in is equal to M dot out. So I can take M dot into factor. Okay, I will take M dot into factor, and then I will do the expression M dot times. What do I do if you remember? So I should do enthalpy, okay, plus V square over 2 plus Gz. So first we should consider this at the inlet. Okay, so let us take M dot into factor because M dot inlet equal to M dot outlet. So we should do H plus V square over 2 plus Gz at outlet minus H plus V square over 2 plus Gz at the inlet. Okay, and now we will try to find what are the known parameter and what are the unknown parameter. So this is our equation. M dot times, now for the enthalpy H we'll divide it into two parts because we know H is internal energy plus P over rho. Okay, so for each term we'll do delta at 2, which is the outlet, value at the outlet minus value at the inlet. So we have first M dot times internal energy at section 2 minus internal energy at section 1, and U2 minus U1 is given. In the problem, they gave us the variation of internal energy. Okay, so we can just replace by its value. Now, concerning the second term of enthalpy is P over rho. So we should find P over rho at state 2 minus P over rho at state 1. Okay, so here what we can do, the pressure P1 is given, it is 18 psi, and the pressure at section 2 is also given. Now concerning rho, since it's water, okay, so we can use the value, rho is constant between the two sections, okay, we can use the common, so for rho, you know that for water, rho is 1000 kilogram per meter cube. And of course, rho can, in general, can vary with temperature, but since we are dealing here with, if you want, for water, okay, the variation of rho is very negligible. And you need to apply very large variation in temperature to have a change in rho. Okay, this is why when you don't have any information, you just use the conventional value of rho, which is 1000 kilogram per meter cube, and just you have here to convert to specific units because you are not working in SI system, you are working in English system. So just you should have simple conversion. Okay, or you can directly use the value of rho in English system. So now, second step is to continue with the terms. They told me I have V2 square over 2 minus V1 square over 2. What about velocities? Do I know anything about velocities? I go back to the given. Okay, they gave me a very important information, which is the rate. Okay, I have the rate. Whenever I have the rate, Q dot. So if I have Q dot is V times A. And if I know Q dot, I can deduce M dot because M dot is rho VA. So it's rho times Q dot. Okay. So here I have an information about the rate. So all I can do is to apply it on inlet and outlet. Okay. So I can say that M dot is equal to rho times Q. Q is given. So all I have to do is to multiply it by rho. So here you can see how we are just, all of this work is for conversion of units. So when we talked about units, okay, for units, you know that slug is a unit of mass in British system, okay, and feet also. Feet is corresponding to meter in SI. Now we have to convert to be able to work in engineering, in English engineering system, which will work with LBM as mass and not slug. Then we will have to convert to do appropriate conversions. Okay, so here all the work done here is just to convert from one system of unit to the other, and it's very simple, and just to use the rules of conversion. So what is, for example, we know that 32.174 lbm is one slug. So if you want to convert from slug to lbm, this is what we will do. We are doing this because here they gave us information. Okay, they gave us the variation in internal energy. They gave us as feet times lb per lbm. Okay, so they are working in English engineering system. This is why we should make sure to have the proper conversions for all terms. So for all terms, we should convert mass from slug or from kilogram to lbm. We should convert length from inch or meter to feet. Okay, and for the fourth, the unit is lb. So by doing so, and of course here for the unit here, for gal, we should convert it to feet cube. Okay, and for minute we should convert it to second. In this way we'll be in English engineering units. Now since we know the value of Q, then all we have to do is, for finding velocity, we can say that Q is V times A. And here Q is constant. Why? Because from continuity equation, so since it's a steady application, m dot n is equal to m dot out. Okay? But we know that for water, which is an incompressible fluid, we can rho is constant, and we know that m dot n is rho times Q. So rho times Q dot n is equal to rho times Q dot out. So what will happen for rho? What will happen for rho is that it will be simplified because rho is constant. And then for an incompressible fluid, you can always say, when I have a steady flow, m dot n equal m dot out and q dot n equal q dot out. While if it's an incompressible flow, this will always hold on for steady application. M dot n will be equal to m dot out, but q dot n will not be equal to q dot out, but you will write rho n times q dot n equals to rho out times q dot out. Because when you have compressible effects, the density can change. Okay, so since here it's incompressible, so m dot n equal m dot out and q dot n equals to q dot out. So I can simply, since I know q and I have the diameters for the cross section 1 and cross section 2, so simply the area is pi d1 square over 4 for a1 and pi d2 square over 4 for a2, and then I can calculate v1 and v2. And now going back to my equation, what do I still have? I have plus g times z2 minus z1, but they told me in the equation that there is no change in elevation between the inlet and the outlet. This means that z1 equals to z2, and this term will cancel out. So I don't have change in elevation. So the variation of potential energy is 0. Now, as we can see, all of these terms are known. We have determined all of these terms, and this is equal to Q dot in plus W dot shaft, which is coming in. Okay. Now, since they told us it's in adiabatic flow, when they say adiabatic, this means there is no exchange between the control volume and the outside environment. So since it's an adiabatic flow, Q dot is 0. There is no loss of heat from the fluid to the environment. And therefore, the only term here is W dot shaft. And now, all I have to do is to replace all variables numerically, and I can get the net work of the shaft. So this is the work rate of the shaft. Okay. Another problem. A steam turbine generator unit is used to produce electricity as shown in the figure. Assume the steam enters a turbine with a velocity of 30 meters per second, an enthalpy H1 of 3,348 kilojoule per kilogram. The steam leaves the turbine as a mixture of vapor and liquid, having a velocity of 60 meters per second and an enthalpy of 2,550 kilojoule per kilogram. So as I told you, in general, okay, if they give you information of the enthalpy directly, you can use it, or you can use thermodynamic tables. So instead of enthalpies, I can provide you with the temperature. So if they tell you what is the temperature of your water, you can determine then what will be its enthalpy by, so you can, they should give you temperature and pressure. So because for thermodynamic tables, you need two properties. Okay, you need two properties if you know that, let's say, if you have, you know, it's water, then you have to know what is the temperature and what is the pressure, and then you go to your thermodynamic tables, you select the entry corresponding to these two conditions, and in the tables I told you that for this temperature and for this pressure I have the following property for my fluid. Okay, now in the next step, in case you have a mixture of vapor and liquid, then you are in a change of phase. If you have a change of phase, then it's enough to provide you with one property, or temperature or pressure. Because when you have a change of phase, okay, then you can determine directly from your table what will be your state. Okay. So in general, since here we are considering fluid applications, we'll not go in detail over thermodynamics applications. We will give you the values of input. Okay. So, but you should know that in general, you can get them from tables. So what I will do now, I will go to my I will go here to my energy equation and apply it. Okay, because what my purpose here is to determine what they are asking me to determine what will be the work output in volts per unit mass of the steam through flow. So we said that for my turbine will deliver work, and my purpose here is to determine what is the work output. Okay, so if I want to determine what is the work output, then I'll have the following. So we use a control volume that that first will include the steam turbine from the entrance to the exit, and then we will apply the energy equation for this control volume. Okay. So then what will happen is that first I have and since also here I have a steady flow, okay, because I have the condition given as uniform for inlet and uniform for outlet without any change with time. So it's a steady application. Then no transient term will figure out. I have one inlet, one outlet, and I have uniform properties at inlet and outlets. So all I have to do then is to apply my formula. That is a Q dot plus sum of Q dot plus sum of W dot equals to M dot times the variation of energy between the outlet and the inlet. Okay. Now concerning my Q dot, again, they are telling me that I have a adiabatic flow, so Q dot will be 0. Now here what will happen is that my turbine will deliver work. Okay, so it's plus, it's plus W. You know in general, okay, that my convention is the following. I put minus W dot. And when I put minus W dot, okay, I have that the turbine is, since it's producing work outward, in this convention, W dot of the turbine is positive. So in total, I will have minus WT. And you will expect that at the end, since your when you have work that is going out, okay, you will have the energy of your outlet flux will be lower than the energy of your inlet flux. This is why when you do this balance, you will get a negative result. So when you do m dot energy out minus energy in, you will get a negative value, which is equal to minus W dot turbine, and you can deduce what is W dot of your turbine. Okay. Now, what we will do, okay, is that we will just replace the values. We'll replace our values here. So we have first, um, for H2 and H1, they are given. And here we are working in SI units because they gave us the values of H1 and H2 in kilojoule per kilogram. Okay, so we are working in SI units, and then our velocities will be in meter per second. And you can convert all your units to joule per kilogram, or if you keep them, if you keep H in kilojoule per kilogram, then your net work output will be in kilowatt. Okay, and if you keep your energies in joule, you will get your total work output in watt. So just be consistent with your units. If you use for everything kilojoule in your energy terms, and you multiply by m dot, which is in kilogram per second, you will end up by kilowatt. If you use joule per kilogram, you will end up with watt. Okay. So now H2, H1 are given. What about V2 and V1? Also, they gave us the velocity at the inlet and the velocity at the outlet. So here also it's very simple. We can directly apply. And in case they didn't give the velocities, they should give information for us to be able to find the velocity. So like in the previous problems, they can give us the mass flow rate or the volumetric flow rate, and we can deduce from it velocities. But here they directly gave them to us. And concerning the change of elevation, they told us that neglect any change in elevation. So the term delta Z will cancel out. And they said that the flow through the turbine is adiabatic. So Q dot is 0. Okay. So now, by replacing, okay, by replacing into our equation, we can see that the net work of the turbine, since they asked to find it per unit mass, okay, so we'll divide W dot, we'll find by m dot. So if we take m dot to the other side, okay, we can find the work output per unit mass. Now, what is the unit of work output? The unit of work output, as I told you, if you use the values in kilojoule for H, if you use kilojoule per kilogram, okay, kilojoule per kilogram, then you will obtain your the value of your W dot will be in kilowatt, okay? And kilowatt represents what? Kilowatt is kilojoule per second. So when you divide by m dot, okay, when you divide by m dot, what should you obtain? M dot is in kilogram per second. So as expected, when I simplify seconds, I will get my work per unit mass, okay, as kilojoule per kilogram, which is the same unit of H. Okay, so now all I have to do is to replace numerically. I have the values of H1, H2, V1, V2. So by application, numerical application, I will get the work output per unit mass, and my final unit will be in kilojoule per kilogram. Okay. So this is about the conservation energy law. Thank you.